All right, back from break. Again, thanks for your patience. I got a little carried away with the first part of today's class. So we were looking at the probability functions for the 1s and 2s, and then we're asking what happens with 2p's, for example, where we do have angular momentum. In these examples, when we walk around the nucleus, what we find is that there are angular dependencies. There are directions where the probability is pretty high. So in this particular state, for the L equals 1 state, where m sub L is equal to 0, the m sub L equals 0 state actually has a lobe of probability and another lobe of probability separated by a plane of 0 probability. So the probability here is pretty high, probability here is pretty high, but not much out in these regions. And at the level of electrons inside atoms and molecules, that is what determines angular momentum. So angular momentum is determined by, if I do a walk around, how much variation do I see as I go around the nucleus. Now it turns out, this is kind of interesting too, in addition to the m sub L equals 0 states, there's going to be some m sub L equals plus or minus 1. Where are their probabilities? And these probabilities match. And you would think, wait a minute, that's not right. Each quantum state needs its own region of space. How is it possible that the m sub L equals plus or minus 1 states both fill in this donut-shaped region along the xy plane? And if we step back and look at the wave function itself, the m sub L equals plus or minus 1 correspond to two different wave functions, one which is rotating in the positive direction and one which is rotating in the negative direction. So angular momentum at the level of electrons inside atoms and molecules has to do with the wave function becoming a traveling wave. And that traveling wave is either circling in the positive direction or the traveling wave is circling in the negative direction. It's all mathematical, but that is what angular momentum corresponds to for electrons inside atoms. Kind of interesting. When we square those traveling wave patterns, they become static wave patterns. They're no longer traveling. They are fixed probabilities that kind of fill in this donut shape. So that's how it works. And it's all being predicted by solving the Schrodinger equation. Okay, let's take a look at some X-ray transitions. So what we're going to do is we're going to take a look at not hydrogen. We've talked about hydrogen a lot. We've used hydrogen to develop the whole periodic table story. Let's move on. Let's look at some heavier elements and ask what has happened. Iron, for example. Let's say here's the 1s state in iron. Here's a 2s. Here's a 2p. Let's say that we have an electron in a 2p state in iron, and it drops into the 1s state. That's going to release a photon. That's going to create a photon with whatever the energy differences are. What would the energy differences be? And in these high energy transitions, the energy of the photon is the energy of state 1 minus the energy of state 2. Now, as an estimate, what we can do is this. We can say iron is element number 26, but for an electron dropping into a 1s state, there would have to be a vacancy. So the first thing we would have to do before this transition can occur, we would have to remove an electron from the 1s state in iron. Now that's not going to be easy because iron is element number 26 and there's a nucleus there with 26 protons in it, and it's holding onto those 1s electrons very firmly. So what we do is we generate a high energy beam of electrons, run them into a sheet of iron, and And those high energy electrons can be high enough that they can create vacancies deep down in these lower quantum states. So some of those high energy electrons are going to remove 1s electrons. Pretty quickly, other electrons from above come and fill in those vacancies. So what we can do is we can take the 26, the Z for the iron, subtract off 1, and get 25. Now, the argument for creating a Z effective, that is 1 below the actual Z, is that when 1 electron is removed, 1 electron remains. And so an electron dropping from, say, energy level 2 down into energy level 1 is only being screened or shielded by 1 electron. There is a nucleus here, there is 1 electron surrounding the nucleus, and then these level 2 electrons are well away from that. And so what we do is, instead of putting in Z squared and getting an exact answer like we did with hydrogen, we're going to put in Z effective, and it's going to give us an approximation. So our estimated energy for that 1 remaining electron in iron is minus 8,500 eV. And the estimate for the energy of the electron at level 2 is minus 2125 eV. Now if you look at these formulas, I know what happens is you think, well, they're not completely consistent with these formulas, but again, they're just approximations, and by using the Z effective approach, we can solve for the energies of the photons, and we can compare that with experimental observations. And we find out that this Z effective approach, it works pretty well. So we just get a Z effective for the entire transit. We don't get separate Z effectives. You would think, well, isn't there a Z effective here and a Z effective here? And I would agree with you. There should be. In more detailed models there are. But in the simplest models, which is what we're going to work from, we just use the same Z effective. We take the Z for the element, subtract off 1, and do all the calculations from there. The prediction is that the photon energies will be 6,375 eV, and that the wavelength of these X-rays will be 195 picometers. Okay. So I'll pause there just a bit, okay, and then we'll move on. Here, we're going back and just restating some of the stuff that we've been talking about. Electrons are not following circular patterns. Electrons are best representatives, our best understanding as to how to represent electrons is a probability distribution surrounding the nucleus. This is an example of a formula for the 1s state. What about the potential energies? The potential energy that we used for the Schrodinger equation was our electric potential energy K Q1 Q2 over R, and the potential energy looks like this. So that's a potential energy between the electron and the proton. The kinetic energies are going to be given by h bar squared over 2m times all of these partial derivatives. And then the potential energy term is right here. So again, going back and reviewing how did this whole Schrodinger equation come about. And then here are the formulas for the angular momentum. So the total angular momentum is represented by L plus 1, square root, times h bar, where h bar is in units of angular momentum. So we can think of that as a standard set of angular momentum. The amount of angular momentum in a particular direction, if we just look at one component, instead of the magnitude, the overall magnitude, if we just look at one component, that quantizes into values of m sub L. Now, what this is showing is, let's take a look at what would happen if L is equal to 2. That would give us a certain amount of total angular momentum. And then the m sub L values could be 2 or 1 or 0, -1 or -2. Those will all correspond to different angles. So what we've got now is a vector. This is the length of the square root of 6. It's L plus 1 square root, which is a little bigger than 2. It's like 2.45. So the total magnitude is like 2.45. The z component is 2, and that gives us a little bit of a tip. So it says that in the m sub l equals 2 state, the angular momentum in general is oriented in the positive z direction. In the m sub l equals 1 state, it's still oriented in the z direction, but not as much. In the m sub l equals 0 state, all of the angular momentum is in the xy plane. None of it is in the z, but it's indeterminate as to how much is x and how much is y. And then we see kind of the reflected pattern with this. So it's going back and looking at what that angular momentum means. Now remember, angular momentum is going to be quantized. And so in a magnetic field, let's say that we've got, this is a 3 SPD state, so we've got a 3D state that the electron is in, and down here we have a 2 P state. So we're going from 3D to 2P, and in a magnetic field, that angular momentum will show up as an energy difference. So if there's no electric field and there's no magnetic field around, these angular momentum directions don't make a big difference. But in a magnetic field, they do. These are charged particles, so the electrons have charge to them. And if there's a steady, not really a flow, but if you could almost think of it that way, of the electron distribution flowing around the nucleus, that's going to generate magnetic forces, magnetic fields and magnetic forces. And that means that if there's an external magnetic field, those different states will end up with slightly different energies to them. Okay, so in a magnetic field, the energy levels split. The energy spacing becomes more complicated. Same thing with spin. So spin has the same sort of effect going on. The spin up and the spin down, if there's no electric or magnetic field around, those have the very same energy. But if there is a magnetic field around, they will have somewhat different energies to them. Okay, here are those 4 quantum numbers. The little n is called principal. The little l is orbital angular momentum. Now the m sub l and the m sub s, the little m stands for magnetic because that's observationally how they were first identified. But you can think of these as one component. So this is one component of orbital and one component of spin. Now we've added in that overall S value for the spin angular momentum. Okay, what are the possible states for n is equal to 3? Let's take a look and see. So going back and looking at these quantum numbers, here is n is equal to 3. If we're on energy level 3, the angular momentum, the orbital angular momentum could be 0, 1, or 2. That would be a set of S, P, and D states. The m sub l values, we would have to correlate those with the L values. Every electron has an overall spin of 1/2 with orientations plus or minus 1/2. So we would get, there would be 2 3s states, there would be 6 3p states, same as what we've looked at before, and 10 of the 3d states. That says at a value of a principal quantum number, n equals 3, there are 18 possible angular momentum configurations. 18 possible states at energy level 3. Here's another example. What about n is equal to 3? Well, if all we're told is that n is equal to 3, then the energy of that state would be our 13.6 eV divided by n squared. N is equal to 3, that leaves us at minus 1.51 eV. So if this is hydrogen, then all the states are going to be at minus 1.51 eV. If it's a heavier element, then it's more complicated. The total angular momentum, if little l is 0, 1, or 2, plugging into this formula, for 0 we get no angular momentum, but for 2, I'm sorry, for L equals 1, we get 1.41, the square root of 2, and then this is the square root of 6. So you can see these are larger than just the integer values themselves. And then the m sub L values are going to be given by these. Now, if L is equal to 0, remember the m sub L's can only be 0. If L is equal to 1, we're limited to these three states. It's only when L is equal to 2 that all 5 of these would be possible, and then spin works the very same way. We can plug 1/2. Every electron has a value, there we go, 1/2. Plugged into that formula gives us 0.866 h bars total, and then the spin up or spin down orientation along one of the axes will be plus or minus 1/2. Now, there are favored transitions for the electrons. Electrons carry angular momentum with them. They tend to go from one state to the other where the L value does change. And what that says is rather than going directly from 2s to 1s, it's more likely to drop from 2p to 1s. Here is the 1s wave function that's given. So this is n is equal to 1, L is equal to 0, m sub L is equal to 0. Those are the wave functions that we have. These are the, this is the probability per shell. Now the textbook, kind of interesting, the probability per shell for the textbook, this is 4 pi r squared. They've canceled some pi's here. It's nice to see the factor of pi here and then the factor of pi here for the normalization, and that's what the probability looks like. So again, it's repeating a lot of the stuff that we've looked at before. What would be the most probable radius in hydrogen? To solve for this, what we want to do is see where this function reaches its peak value. So this is the probability per shell. To find out where it reaches its peak value, what we can do is take a derivative of that expression. So taking a derivative, setting it equal to 0, gives us r squared over a equals r, and says the most probable distance would be at r is equal to a. So the Bohr radius turns out to be, it's not a, there's not a circular orbit that the electrons are going through, but if I look at the probability distribution per shell reaches its maximum value at the Bohr radius. Now, this is a difficult example, so it's asking how would we calculate the probability of the electron being found within 2 Bohr radiuses? So let's think about this. Here's the proton. It's hydrogen that we're looking at. It's the simplest possible state in hydrogen. Here is the electron distribution. And it's 4 pi r squared times the wave function squared, dr, evaluated from 0 to 2a. And what we're going to do is, I'm not going to go into the real details here. I'm going to do a variable substitution. If you're, if this is something you want to follow along with, that's great. But basically, we're just finding out, of the total probability, which the total probability would be 1. If I only integrate out to here, how much of the probability am I including? When we carried out the calculation, we got 76%. So about 76% of the probability in the 1s state in hydrogen is within 2 Bohr radiuses. And that says that 24% is beyond 2 Bohr radiuses. So that's kind of interesting. We think of the Bohr radius as representing the size of hydrogen, but 24% of the electron probability extends beyond that distance. Okay, here are some better diagrams. So here are their diagrams of these different states. here are what the p states look like. Here is the n equals 2, L equals 1, and m sub L is equal to 0. Here are these lobes on either side of the xy plane. And then this is what the m sub L is equal to plus or minus 1 look like. And those are these donut shapes with most of the probability in and around the xy plane. We've talked about the Pauli exclusion principle. Every electron needs to have its own quantum state. And so here's how we're going to fill those states. So what's going to happen here is for the 1s state, here's a spin up, spin down. That's two possible states here. So hydrogen would have one of these electrons. Helium would have both states filled. Lithium would have both of the 1s states plus one additional electron. Now jumping ahead to sodium, which is element number 11, that would be 2 in the 1s state, 2 in the 2s state, 6 in the 2p state, and then 1 in the 3s state. So sodium is right below lithium in the periodic table. Why are they lined up like that? Because sodium is following the same pattern as lithium, except sodium is starting out at energy level 3, whereas lithium is starting out at energy level 2. So what lithium is beginning to set up on level 2, sodium is starting out on level 1. Lithium has one electron, one unpaired electron, available to form chemical bonds. So does sodium. It's in a different energy level, but because both sodium and lithium each have one unpaired electron available to form one chemical bond, they form similar compounds. If I can make a compound using sodium, chances are I can substitute lithium and form an analogous compound. Okay, so just some more statements about how many electrons, how many quantum states are going to be at each of the different energy levels. So we had said that every electron needs its own set of quantum states. And so for helium, Z is equal to 2, and that means both of those electrons will fit in the 1s state, so that would be n equals 1, L equals 0, m sub L equals 0. It's only when I get to the spin up and spin down where we can see that there's two possible states. If it weren't for spin, there would only be one state available for that electron. What about lithium? Well, lithium's got the 1s states filled. Again, now notice these two electrons have the very same values for n, L, m sub L. It's only when we get to m sub s where we can see the difference between spin up and spin down. And then the third electron needs to go to the next energy level. And then here are those quantum numbers for sodium. Okay. Every electron needs to have its own unique set of quantum numbers, and often that comes down to this last column where we're putting in spin up and spin down to get the pairs of states. All right, let's see. Here is the ground state configuration of sodium. So again, we've seen this with the periodic table stuff that we've looked at. So sodium, we said, is element number 11. If I'm looking at a neutral sodium atom, now this is not a block of sodium, and this is not sodium in necessarily sodium chloride, something like that. So if I think in terms of individual atoms of sodium, maybe a sodium vapor of individual atoms, the electron configurations for those atoms, we've got the 1s state filled, that's 2 electrons. 2s state brings us up to 4. 2p6 brings us up to 10. We completed level 1 on the periodic table. We completed level 2. And then that 11th electron is left by itself on level 3. Okay, and here's what we saw with the different values of L. Each value of L has a different letter symbol that goes along with it. Now it turned out with the periodic table, we were able to place all 118 elements, all the way up to element 118. And for the ground states of those elements, we did not have to include any G or any H state, although those have been identified. So atomic physicists who research involves looking at atoms and the energies of all the different possible states, they are able to excite electrons into these excited states in terms of angular momentum, but the ground states themselves don't require that. We can get to elements 118 without introducing G and H. Okay, here are some electron configurations that we're given. We're supposed to find the problems with these. Okay, let's see. This looks good. 1s2, 2s2, 2p6. Now, this takes us through the first row of the periodic table. These two take us through the second row of the periodic table. That means I'm at element 10. I'm all the way up to neon. Pull out your periodic table and follow along. And then on the next level, I'm going to get 3 electrons. Oh no, but they tried to put 3 electrons in an S state. They won't all fit. That's a problem. So the problem came right here. An S state cannot accommodate 3 electrons. Now if we take one of those out and make this 3s, then it would be element 12, which I think is magnesium. But that's a problem with this electron configuration. All right, let's try this again. Level 1, 1s2. Level 2 looks good, 2s2, 2p6. This is interesting, 3s2, 3p. Now it's not 6, it's not full, but they've moved on to the next level. Is that allowed? That is not a ground state configuration. It's an excited state. What has happened is that one of the electrons from 3p has moved into the 4s state. So that would be, there would be an element, this is what, 18, 19, that's like potassium? Is that right? So this would be an example of potassium where one of the 3p electrons is excited into a 4s state. And then finally, 1s2, that looks good, 2s2, 2p6, so far so good. Oh, 2d, there is no such thing. At level 2, there is no angular momentum state of d. So the 2d doesn't exist. Oh look, and that's what we ended up with. So here we said that for S states, there's only 2 possible states. There is an electron missing here, but we could think of it as having been promoted. And again, I think this adds up to 19. I think that's potassium. Yeah. And then the 2d doesn't, there's no such thing as a 2d state. Okay, kind of fun to take a look at those electron configurations. So this is just outlining the properties of elements in the periodic table. These slides have a lot of just writing to them, and that's why I had kind of put together my own and worked mostly from those with more diagrams. But this is repeating stuff that we've seen before, so it serves as kind of a review. And when we were looking at X-rays, we said that the effective charge that an electron sees is the charge on the nucleus, but shielded by the inner electrons. So if I start out with an iron nucleus, there's 26 protons there. If I surround that with a couple of 1s electrons, and then I step outside, well now I only feel the effect of 24 protons. 2 of those electrons are shielding the nucleus. So as I move farther and farther out, the outermost electrons only feel a nuclear charge of 1 or 2 because they're being shielded by all the other electrons. So the inner electrons feel the full effect, but the outer electrons only feel a charge of, a couple of positive charges. And that is, that kind of outlines the properties of binding energies for these electrons. So as you move through the periodic table, the binding energies don't vary a lot. there's always going to be some set of electrons that are not being held on very securely, and so you can form compounds with elements throughout the periodic table. It's not that as you get more and more protons in the nucleus, at some point the electrons will not release. There's always going to be electrons in the outer regions that are shielded by the electrons in the inner regions, and that will allow those electrons to form chemical bonds. Now here are the some of the graphs with the X-rays, and so what we're seeing here is these different transitions. Now this is in terms of wavelength, so if wavelength is increasing, if this is longer wavelength, then this is higher energy. So this is the lowest energy transition with a peak, and what that is it's a 2-to-1 transition. It's n equals 2 to n equals 1. This is likely from n equals 3 to n equals 1, but this is what these X-ray spectra look like. When we shoot an high energy electron beam at these materials, they remove the inner electrons, and as other electrons drop to fill those vacancies, we get these X-rays generated. So this is showing numbers of X-rays being generated. This method works so well. You know, you would think this is just kind of a rough method, but it works well enough that when the periodic table was filled in, it was discovered that there were some uncertainties. You know, when you get through those metals, the transition metals and the inner and outer a lot of these metals have very similar chemical properties. It's hard to place them in the periodic table purely by their chemical properties. What they could do is they could send X-rays into each one of those, and as the number of protons goes up, the gap between state number 2 and state number 1 steadily increases. So this energy of K alpha and K beta both, they're just going to steadily increase from one element to the next. And that's what this next graph is trying to show. I'm not sure how successful it is, but it's showing that as Z goes up, 1 over the wavelength increases. And it turns out that the last several elements in the periodic table were successfully, their location was successfully identified. It was figured out how many protons they had by using an X-ray technique. Generating X-rays allowed them to sample the spacing between n equals 2 and n equals 1, and that steadily increases with increasing number of protons. Z is what we call the atomic number, and it tells us how many protons there are in that nucleus. Okay, here's an example back to using X-rays with molybdenum. Let's see how this works. Molybdenum is element number 42. As we were saying before, to get Z effective, I take the actual number of protons and subtract 1. And then I think in terms of the electron dropping maybe from a 2p state into a 1s state, and that difference in energy will get bundled up and generate, it's going to create a photon. So the energy of the lower state is my negative 13.6 times my Z effective squared, divided by 1 squared. If I move to state number 2, again, I'll use my minus 13.6 EV multiplied by my very same Z effective squared, but this time I divide through by 2 squared. So state number 2 is calculated to be at minus 5700 EV, but that lower state is at minus 22,860. Again, as we move through the periodic table, every time we move to the next element, the Z value has gone up by 1, which means the Z effective goes up by 1, which means the E1 drops in energy and the E2 drops, but the E1 drops more. And so the spacing between these two, as they both get deeper, the spacing between state 1 and state 2 increases, and from that we can determine which element we're looking at. For molybdenum, this is making a prediction that the X-ray produced in going from level 2 to level 1 will be somewhere around 17,000 eV. So you think back in hydrogen, going from state 2 to state 1 was 10 eV, but in molybdenum it's 17,000. You can see the spacing between the energy states has gotten significantly higher. And then using our formulas, lambda equals hc over energy, we can determine what that wavelength would be also. Okay, here's another example with the X-rays. This time we're figuring out which element it is. So we have a sample of some element. We're trying to determine what is the Z value, which element is it. We do an X-ray test. We find out that the 2 to 1, the K alpha line, has an energy of 66,000 eV. That's pretty high spacing. So 66,000 eV between these two states. And the wavelength there would be 18.8 picometers. Now, what we can do then is we can set up the formulas. This is what the energy of state 2 would be given by. This is the energy of state 1. They both have a factor. Oh, that's Z effective squared. Oh no, put a square right there. So Z effective squared, Z effective squared. I can solve this formula for Z effective squared. And this is going to be 66,000 divided by 13.6 times 4/3, which comes from 1 minus a fourth. And so the Z effective here is 80. Now remember, the Z is going to be larger by 1. This must be element 81. And it works. It works all the way through the periodic table when we take a look at element identification through X-rays. And then this is just showing that, when we looked at the X-ray, when we looked at this, notice we're not just getting X-ray lines at specific energies. There are other X-rays being produced, and that's where the electrons are just going through the material. They're not displacing other electrons. But the electrons are interacting with some of the nuclei and just generating high-energy photons, and those can have any energy whatsoever. So those sharp peak lines show up in addition to kind of this continuous spectrum of X-rays. Okay, what is the shortest X-ray photon emitted in an X-ray tube subjected to 50,000 volts? So let's take a look at this. So we're going to accelerate those electrons. We're going to use 50,000 volts to accelerate them. That means the electrons coming out will have 50,000 eV of kinetic energy. Now, for maximum transmission of energy, let's say that the entire 50,000 eV of the electron is converted into photon energy. So somehow the electron goes in, it interacts not with other electrons, but maybe with a nucleus, and it's going to generate a photon at 50,000 eV. Well, the wavelength of that photon would be 24.8. So the energy of the photon coming out is not going to be any higher than the energy of the electron coming in. And again, if we come back to this picture, that would be the cutoff. The cutoff for the production of X-rays, of high-energy photons, will not be any higher than the energy of the electrons in the beam using to generate those X-rays. Okay, let's see how we're doing with time. We've got some time left here, so let's look at a couple more topics as time permits. I think we've looked through the bulk of the topics that we're really interested. So these are just a couple of additional examples that we're going to look at. The first thing to be aware of is, and we've mentioned this before, since we're dealing with charged particles, so the E here represents, this is an electron charge, this is the electron mass. Anytime we have angular momentum, whether it's spin or whether it's orbital, we're going to have a magnetic dipole set up. It's a charged particle. It has angular momentum. That will generate a magnetic field. So the electron will feel the effects of surrounding magnetic fields, and it will also generate its own magnetic field. So both sorts of things are going on. And then what this is showing is that we can break that magnetic dipole down into, we can quantize it. So what happens as a result, and again, we're not even paying particularly close attention to the formulas here. They're a little beyond what we're interested in, but this is an interesting feature. So let's say that here's an oven, so we're vaporizing atoms, and the idea here is, I think this was first done, I want to say it was done with silver, that ovens were used to produce vaporized silver atoms, and that the silver atoms have one leftover electron in a, I want to say it's a 5s state, I think. So there's a leftover 5s electron, and that one electron going through a magnetic field, the spin up and spin down variations get pulled in opposite directions. Because the spin up and spin down are going to be drawn into the magnetic field differently. And so based on the spin up and spin down, it's going to have a magnetic dipole that is oriented in one direction or the opposite direction. And in a magnetic field, those two different dipoles will get pulled in opposite directions. Now what you would guess is that there's going to be a continuous spread of the electrons, of the atoms, going through the magnetic field because it's kind of a random thing. The orientation of the spin could be in many different directions. And what this is showing is that interaction with the magnetic field actually results in the atoms committing to one quantum state or the other. So the electrons up to that point, you know, they could go, well, I'm kind of 50-50 whether I'm spin up or spin down. But going through the magnetic field, the electrons end up deciding whether or not they're spin up or spin down. The spin ups get pulled in one direction, the spin downs get pulled in the other. And instead of kind of getting a smeared pattern, we end up with two fairly distinct lines as to where those atoms are going to be landing, two distinct locations on the screen. So again, this was an experiment done that first suggested the existence of spin, and it reinforced the idea of quantum states and what happens when atoms pick a particular quantum state to go into. We can take the overall angular momentum, we can add the orbital and the spin angular momentum together into what's called total angular momentum, and often that goes by the symbol J. Now it seems funny at this point, but you can actually show that there's a consistent way of taking the L's and the M sub L's, the S and the M sub S, and defining J's, all the possible values for the combined angular momentum. Again, this is a topic that's kind of beyond. Take a look at the homework, and you will be able to see the topics that we're most interested in. Fluorescence and phosphorescence. Sometimes what happens is when we have a photon that's absorbed, it's possible that the electrons get stuck in certain quantum states, that there's not an easy transition back down into a lower state. So this is showing that you could have a photon that's absorbed, and it could drop down in 2 steps instead of 1. So you'd end up with more photons being generated on the way towards de-excitation. And then with fluorescence, there is the possibility, and I don't know if they have a good diagram here or not. Okay. What can also happen, I'm just going to work from this one, is that you can have electrons that go into a higher state and they become stuck in a higher state. Maybe they transition to a state here and there's no easy path to get from this, or no very likely path. It becomes less probable for this to transition back to the ground state because of the mathematics of the wave functions. We can go in and look at the wave functions and see which transitions are likely and which transitions are not as likely. And so you can have electrons that are excited in these phosphorescent materials that will glow in the dark. And that's because the electrons are dropping back down into the lower state, but they're doing it kind of on their own time. And then lasers. So lasers, I think this is probably our last topic here. So lasers, here is a photon coming in. I know it's a squiggly line, but I'm imagining it to be straight. So here is a photon coming in with some amount of energy, and it's taking electrons from lower energy states and placing them in upper energy states. Now, if this becomes a state where the electron does not have an easy way to collapse back down, then what can happen is, if we send in a lot of photons with just the right energy, we can get a lot of electrons in those atoms in the excited state. So you've got a bunch of electrons all sitting around in the excited state with no easy way to drop back down. And what you can do is you can set off the release of all of these electrons by sending in additional photons of the right energy. So you can pump a bunch of electrons into a higher state, and then you can send in an additional photon and get all of the photons to release together, kind of at the same time. And that is what makes up a laser. Laser is an acronym. The SE is for stimulated emission. So here is the normal population of electrons, many, many electrons in this lower state, not very many electrons in this excited state. And then what's going to happen here is we're going to send in photons that push electrons into these excited states, but they're going to be excited states where they're kind of trapped. There's not an easy way for them to drop back down. We talk about that as being an inverted population. And then by sending in photons of the matching energy, we're able to get all of those electrons to drop together, and that gives us a laser. There's a couple of other examples of lasers here. This is one that in lab, the lasers that we've been working with are helium neon lasers. In the helium neon laser, we first of all send in photons that move electrons in helium into an excited state. From the excited state, when the helium, when we have collisions, interactions between the helium and the neon, we're able to take the energy of these electrons and use them to excite an electron in neon. And then from this state, this is actually where the red helium neon laser light is coming from, is this transition within neon. Now, it's not all the way back into the ground state. The ground state is much farther below, but there's this transition between two states within neon, and it's done by, first of all, pumping the helium, so the electrons are in the excited state, allowing collisions to take place, which the helium electrons drop back down, but in their place now we have pumped electrons into the neon excited state. And then there is this transition that we can set off with sending in photons of similar energies. We can set off that effect of stimulated emission using light. And of course, lasers are used all over. Surgery and machining, surveying, barcode, CDs, DVDs. And then that's it. So holography is another interesting effect. I'm not going to bring up anything with holography here. So that takes us through chapter 39. So, and again, you know, for us, take a look at the homework problems. It's this, well, the stuff that we really spent a lot of time on in the earlier part. That's a good example. You know, the hydrogen wave functions, we spent a bunch of time looking at those. So anyway, if you guys have questions on any of the stuff from the chapter, stop by office hours and we will get those looked at.